Let's take another look at this neural netverse, the neural network of the universe. And this time, we're going to be looking at the linear inputs where we got our groups 1 times 1, 2 times 2, 3 times 3, 4 times 4. We kind of see them as U1, SU2, SU3, and then we have this spin 1, 3. And, well, the output of everything is going to be just the regular old standard model. Hopefully, we'll even find some neutrino masses or dark matter in here. The idea is that we're going to follow a cohomology to do a nonlinear activation. You technically get this little anomaly by applying this cohomology structure. So in the first situation, we have this idea where you have U1, and well, this is the equation. The idea is you have this H, and then there's a dimension plus 2, so we're in dimension 4. So really the only H that matters is H6. So let's go over to our line here of H's. I've already sort of calculated some of these H0, H1, H2, H3, H4, H5. But this one, H0, is just going to be Z. And then it kind of follows this formula where you have H2, you're going to toss in um, your C. This is the first Chern class, and then you get one of those. So every even one, you're going to get an extra first Chern class. Then you go to the H4, and you get a Z times a C1 squared. Now, this doesn't make a lot of sense, of course, but you know, it's the math that makes everything work properly. And over here in the third one, which is the part that matters for d equals 4, fourth dimension, we're in t, x, y, z. The only thing that matters is h6, and that gives us this cubic first Chern class. So what we need to do is make sure that the cubic nonlinear activation layer basically gets canceled. This little anomaly gets canceled. Yeah, this is basically like a neural network where each linear input, we've got our linear input of 1, 1, the U1 group, and output is going to be this very tight restriction that we have to have on this particular layer. It's the cubic activation. So you sum up the cubes of the hypercharges. Interesting. Now, for the next one, we go to 2, 2. This is going to be SU2. And it's interesting because the local anomaly here is actually gone already. So that's not really what gives us the nonlinear activation. Well, what we have to do is look at the 5-dimensional topology and sort of see what happens from above as you start to make rotations one extra dimension above. And well, it turns out that you get this weird thing. This is discovered by Witten, and he basically said that you have to have an even number of SU2 doublets. I mean, this just kind of makes sense. This is the math that proves it, but this is the term that just says you have to have an even number of SU2 doublets. All right, so this is the parity activation, the second layer. And we input SU2, and out comes this even doublet rule, even number of doublets. If we go to the 3x3 here, we've got SU3. This is the linear input for this layer, and we're going to get this strange pairing situation. Where kind of depends where you're at. So at H0, you're going to have a Z. At H4, you're going to have a Z C2. And then H6, which matters for our four-dimensional spacetime, is going to be Z times C3. This is the third Chern class, and basically all we get is this situation where we have to balance the number of triplets with the number of anti-triplets. Alright, so that's going to be our balance activation. Now we can go to the fourth layer, which should be our final layer for this particular round. We're going into the linear input 4x4 here. We get the spin 4 group, and again the pure anomaly cancels. But let's look at the second part where we have to do this little combo. So we're going to look at the curvature of the 2 form here, the 2 form curvature, and then multiply that by the trace. So basically you get this situation where you get a linear activation because traces are all just linear numbers, just scalars. So you're just going to add up all the scalars here and you get a linear activation. So these are the 4 types of activation layers. And when we get our inputs here for our SU1, SU2, SU3, and spin 1, 3, then, well, we get this nonlinear activation at each stage, the cubic, the parity, the balance, and the linear. And this is another way that we can look at the standard model and how we get these outputs of certain things. We basically have this decision tree where all these branches are sort of popping out, but these very specific nonlinear activations are causing only one branch to survive, and that's this one right here. So this is the neural netverse, neural network.